All right. So yesterday we talked about the quantum mechanical model. It's the upgraded model from the Bohr model. It's got 4 layers. Honors is learning all 4 of the layers of the organization scheme of the 4 layers of the address of the electron. Everybody else though is just required to learn the first 2 levels. Okay. And with those first 2 levels, we created a new writing system known as electron configuration, the way that we write up the address or the location of each electron in an atom that goes past the Bohr model for multiple reasons. One, okay, it goes past the Bohr model in this sense. The Bohr model is a 2D model, whereas the quantum model is a 3D model, okay? It also goes past the Bohr model in the sense that the Bohr model, okay, talks about shells or energy levels, or another way of calling them is orbits, okay? But while it only talks about that, we have no specific location or placement of electrons within those. Whereas the quantum mechanical model, on the other hand, has multiple things. It doesn't just have energy levels. It has 1, energy levels, or principal quantum number is the technical way of saying it. Then it has orbitals, right? Your zones. And then honors, I'm going to switch to blue for honors, is also going to learn about suborbitals, which by the way, prep, I kind of already told you in the last lecture, just because it makes the orbitals make sense, but the different, right, orientations. Okay. And honors is going to learn a 4th thing called about magnetic spin, which is like the specific number on a house. It's like very specific to that electron. You're either up or you're down in the spin of the earth. Okay. The Bohr model also is different and superseded by the quantum model because the Bohr model only acknowledges columns, okay, 1, 2, and then 14, 13 through 18, okay? It only acknowledges those elements, right? Ignoring transition metals. Which, so another way you could put it is ignore like transition metals, like half the periodic table, more than half the periodic table, right? We can't do anything with that. Bohr model ignores all of that. But the quantum model, on the other hand, it allows us to describe all elements, right? Now it allows us to describe all elements, okay? So hopefully that was a similar something that you guys kind of got if you jotted down, okay? But that's kind of where we're at. That's where we left off before you guys took your Bohr model and Coulombic attraction periodic trend quiz or test. And so we're picking up here now. And we started introducing, we went through one example problem on electron configuration, right? The address. And electron configuration, remember, is based off of, in the quantum mechanical model, layer 1 and layer 2. Okay, which would be energy levels and orbitals. Okay, that's what we are basing everything on, right? And I even wrote it down below. I see that I wrote it in purple down below. So, you know, double whammy. And we gave a name to the principle for the first time called Aufbau principle. We gave a name to the idea that we fill from the bottom up. We fill from the lowest energy level to the highest. We gave it an actual name for an Aufbau. And we said, well, we do the same thing in how we write it as well. Like it all translates. It's all consistent. Okay. And so we spent the first example, looking at sulfur. And we said, okay, sulfur, neutral sulfur has 16 electrons. So when I look at my periodic table, okay, I know that wherever I mark the address, wherever I write up the address of the sulfur electrons, I need to account for 16 electrons and where they each go. And I need to be specific in not only what energy level they're in, but what orbital, what shape, what zone they're in, what city they're in, according to our analogy. And so what we did is we walked through, we started from the lowest energy level, which on the periodic table happens to be the top. The lowest energy level happens to be the top, okay? And we fill it as we go. And we account through a superscript, a small upper right-hand corner number, how many electrons are present in that zone, in that energy level, right? So we said for the first zone, okay, it was 1s2. I have 2 electrons in row 1, zone S. That's 2 out of my 16 accounted for. Okay, where are my other 14? Okay, 2s2, row 2, zone S, 2 of them. 2p, as I read across left to right, going down the periodic table, which is really going up in energy levels. Okay, 2p6, 3s2, 3p4, and we do include the box, the electron box, because every box represents an increase in 1 proton and 1 electron for a neutral atom. We do include the box that the actual atom's in. You got to put your butt in the seat to own it. So you include yourself. Yes. We do include helium. Helium is technically part of the s orbital. So technically, helium should be here. Like helium should be there. But helium is a pseudo noble gas because it has a duet and it only can handle a duet. So it's completed. So we put it above the noble gases, even though technically it's an s orbital.
Yeah, so why don't we write S1, S2, and like 1, or like 1, S3.
There is no 3.
But if helium should be over that,
it's still only 2 boxes though in the 1s, 1s2. There's no third box. Every box represents a little seat that an electron can exist in, a specific house that an electron can exist in, okay? A specific one, okay? All right, but thank you for that reminder about helium. That actually is still really important to emphasize. Yeah, helium is part of the S. It's just, remember, hydrogen and helium, VIP, they function differently. Kind of like reality TV stars, like Kardashians, no rules apply to them. None of it makes sense. They dibble and dabble in what is technically socially acceptable, and then they make up their own rules. Hydrogen and helium, they're the VIPs. They're the Kardashians of the periodic table. They kind of make sense and they really don't at the same time. But somehow we all love them and we need them and it works. I don't know why, it just does. Okay, so that's where we left off. And I stopped before things got complicated. We're going to start now looking at where it gets a little bit more complicated in electron configuration writing. Because what if I asked you to write the configuration of tungsten? What if I ask you, oh God, that's not highlighter. What if I asked you to tell me the electron configuration, the address of all 74 electrons for tungsten? I could be real mean and ask you to do radon down here at the bottom, right? Let's just start off kind. Let's do tungsten. We're going to take the same principles. Okay, so I'm going to erase all of this for a second, just to start fresh, clean. And we're going to do the same principles of let's start counting. We need to account for all 74 electrons in tungsten. It's got 74 electrons in the neutral state of tungsten. So what are we going to do? We call this, by the way, expanded configuration when we write every single location. I'm going to teach you a shortcut in a second. Okay, so I'm going to write out the full or expanded electron configuration of tungsten, following the rules that I did above. So looking at tungsten, I say, okay, as I say this, by the way, please write it down. Good God. Okay, 1s2. 2s little 2, right? 2p little 6. 3s2. So far I have 1s2, 2s2, 2p6, 3s2. I have so far 12 of my 74 electrons accounted for. Cool. Okay. 3p6. And remember, it's little 6. If you write big 6, you're telling me that that's a 62nd row. No. Little 6, little electrons. little 6. Okay. 3p6. Everything so far is making sense. 4s2. Now here's where it gets weird. 3d10. And you're like, nuh-uh. Whoa, whoa, whoa. That is in the 4th row. Yes, but no. So every d orbital row, every d zone is 1 energy level lower than you think it is. It's like when you drive on a street and the street seems off and you're like, why didn't they just make a straight street? But they somehow had to shift it down for whatever reason in the planning of the city. Same idea here. 3D, it fits better for energy reasons that I'm not going to get into with you guys. It's way too advanced. For energy reasons, 3D is technically slightly, relatively higher in energy, the 3D orbital is, than the 4S. Even though the overall energy level of 3 is still less than 4. But it comes after 4S. My biggest thing, just learn where to dip. Learn the dip, okay? That's my biggest trick. Don't try to make it make sense. Learn the dip. You're still going to read left to right, okay? Just learn that when you get to this zone in the left to right reading, you drop down for a hot second, then you come back up. Because then what happens is we go up to, and I'm going to highlight this to help you. This is the weird zone. Okay, now we go back up to 4p6. We jump back up to the 4th energy level because we're in the 4th row. Then we keep going. 5s2. What do you think the next thing I'm going to say is? 4d10. Excellent. And so it's another trippy one. Trippy, trip, 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 trip. 4D. Because the D zone is always 1 less energy level than what you think it is. It's always 1 row lower than you think it is in numbers. Then you jump back up to, because we are in the 5th row, you jump back up to 5p6. Okay. Now we go to 6s2. Okay. Now it gets even trippier. We go down to 4f14. 4f14. So these two pulled out rows technically come from here. We just can't fit it on a page, so we pull it out. But it technically is always after the 6 and 7. Those 2 rows come after 6 and 7. And it's always 2 energy levels lower than what you think it is. Again, that's all based off of the energy concept that I cannot explain to you guys because it's not necessary. You just need to learn to accept it. Until you get into higher level chem, I will explain why that's the case. And the quantum mechanical model does explain it, but it's not essential for you guys. So what you just need to remember is once you get to 6s, it gets funkadunk. Okay. After 4s, it gets weird. After 6s, it gets into super funky F zone. Okay. You go from 6s to 4f14. Then you jump back up to the d orbital. But remember, the d orbital is always 1 less than you think it is. So now it's 5d, 1, 2, 3, 4. 5d4. Yeah. Okay. So it goes 1s2. Everything's normal until you hit the 4th row. Then you start dipping. When you hit the 6th row, you double dip. Okay. Yep. Okay. So here's my advice for you. Everyone likes to make the levels fit. Don't. Just read left to right and remember when your numbers change. Don't insert what you think is right on the periodic table. Just read straight from the periodic table, let it tell you. And that will make more sense as you do more practice problems. Okay. The periodic table is the right way, left to right. Do not shift your eyes. Just go left to right. Shift your numbers. Okay. You're not going to shift your eyes. Don't drop your eyes at all. That's not where the change comes from. Your change is coming from the way that you number it as you read steadily left to right. Yes. No, what I don't want you to do is read it and say, oh, look, it's the fourth. It goes up to the third. What people do is they try to put the numbers in their head and they read from the numbers first. They make the numbers fit the periodic table. Don't. Read from the periodic table, make the numbers fit. It's a different way of looking at it. Okay. So that's tungstens, which is quite impressive. Okay. So that's awful, by the way, to write out. And that, if you add it up, is 74. That is 74 electrons accounted for. Their relative energy level, state, and their zone, their city. Okay. But that's a terrible experience for everyone involved. All right. So the question is there a shortcut? Of course. Chemists are lazy. Of course there's a shortcut. Of course, of course. Okay. Chemists are lazy. This is an awful experience for everyone involved. This right here. So what we say is we have a shortcut called the noble gas notation. And because I ran out of room, I'm going to actually go down and put an arrow. Okay. We're going to talk about it here. So the noble gas configuration is your slang for the address. You know how instead of writing California, we write CA, right? Instead of writing Santa Barbara, we write SB. It's like your way of writing the address with slang. Okay. So step one is identify the noble gas element, column 18, that comes before your element. So for tungsten, the noble gas that comes before tungsten is xenon. It has to be before. It has to be before. So for us, it's going to be xenon. What we do is once we identify it, what we do is we put brackets. Put brackets around the noble gas. Okay. What that bracket does is that represents the electron configuration up until that element, that noble gas. So what bracketing xenon does is it helps us go all the way up to 5p6. That bracket encompasses all of that. So yeah, let's see if I can do something. Noble gas. Ooh, that is not great. Okay. That bracket encompasses all of up to here. So we don't have to write it. And then what you do is you pick up where you left off. Okay. Then you write the remaining electron configuration. So it becomes xenon 6s2 4f14 5d4. And now that becomes the shortcut, the noble gas electron configuration for tungsten. This is tungsten. Much better. Much, much better. Much faster. Okay. So we just pick up where we left off. What if the element I tell you to write noble gas configuration for is a noble gas itself? You cannot. Okay. Let's say I ask you to write the noble gas configuration. Good God, new color. Let's say I ask you to write the noble gas configuration of argon. Ar. Okay, you cannot write argon, done. That's a no. That's a no. Okay, that is a fat no. What instead you do is you write the noble gas before it, neon, and then it becomes 3s2, 3p6 for argon. It has to be before it. So helium and hydrogen don't have noble gas configuration. There is no noble gas before helium and hydrogen. They straight up don't need it. But it also doesn't, you don't really need it anyway, because it's just what, 1s2, 1s1. Like that's not going to save you much time, right? You're putting about the same strokes of paper, of ink on the paper. Okay. So it makes sense that noble gas configuration doesn't really exist for hydrogen and helium. Again, VIP, they're in their own class. Okay. So one last thing I want to say is, how does electron configuration help us identify valence electrons? How does it help us identify valence electrons? Valence electrons, yes. Okay. Valence electrons are the electrons in the highest energy level. So here's where you have to think a little differently. When you look at, let's go back to the easier example. Our valence electrons are going to be in sulfur, any electron in row 3, right? Highest energy level. Okay. So what we would say is we have 6 valence electrons in row 3, right? Row n equals 3. That's easy to spot. Electron configuration is also a great way of identifying your valence electrons. But what about when it gets really weird and you have all of this? What's the highest energy level? What's the highest energy level where electrons exist for tungsten? What's the highest row that electrons exist in tungsten? Row 6. Exactly. It's row 6 that are the valence electrons. So your first thought is, oh, the last electrons I account for is 5d, 4. I have 4 valence electrons. No, because valence electrons is about highest energy level. Electron configuration, relative orbital energy, sublevel. But valence is all about highest energy, principal quantum number, state level. Okay, so what we say is that for tungsten, tungsten has 2 valence electrons in row n equals 6. Even though we technically write that the electrons in 4f14 and 5d are technically slightly energetically higher. But valence is not about technical energy level higher or orbital higher. It's about full on just straight up energy level higher. So your valence electrons for tungsten would still have to come from the biggest row number, 6s, and I have 2 of them in row 6. Trippy, right? Trippy. Now, what if I asked you to put a charge onto this? What happens? You add and subtract electrons. So what if I ask you now to do a charge? And I'm going to write in the cracks and crannies here. What about a cation? When we lose electrons, you take from valence. So what I would do is, if I was a cation, I would take from the 6s2. So I would take from 6s2 and I would remove it. And now the tungsten configuration becomes 5p6, 4f14, 5d4. I would take from the valence electron 6s2. Okay, it would be gone. But what about if you're an anion?
So would the whole 6s2 be gone?
Yep, you would just remove the 6s2 from the electron configuration. Okay, so maybe it becomes 6s1. Maybe you only remove 1 electron. Maybe you remove 2, 6s2. Maybe you remove more. You drop down to 5. So when you remove electrons to form a positively charged atom, you remove from the valence, the highest energy level, and then you go down. Okay? Then you remove from the P, then you remove, or actually from the D5, then you remove from the 5P, then you remove from the 4D or the 4F, then the 4D. It gets weird. It gets weird. Okay? But yes.
So just to clarify, when you would write it, it would be 5P6, 4F14, like you would just.
Yeah, you would just take that thing out. Okay? Yes.
Once you're done with, if you get rid of all the valence electrons, you say, and then you rate, you would take away from that first. Then
You would take away from, so this is how the removal will go. You would take from 6S, then you would take from 5D, then you would take from 5P, then you would take from 5S, then you would take some from 4F because you're going by energy level removal. But when you add, it's different. When you're an anion, okay? When you're, I'm just gonna cross this out for a second. When you're an anion and you gain electrons, you add to the next, okay, available orbital. So you follow electron configuration. So what we would do is we would add to 5D4. We become 5D5, 5D6, 5D7, 5D8. We wouldn't jump to 6P yet. We would add to the next available orbital spot. Weird, right? Kind of cool. So, that's how we account for cations and anions in electron configuration. Okay. And remember, cations are positively charged. Anions are negatively charged. They have more electrons than protons. Yes. The five would be the new valence electrons, and it would be actually, it'd actually only be 5s2 and 5p6. So you'd max out at 8. You will not get a question that hard. Like, you won't get a question that hard with valence electrons. You will get an electron configuration this hard on the quiz tomorrow, which is why you're working with partners. You will not get a valence electron count this hard. In AP Chem, absolutely. If you guys are looking toward AP Chem, you learn this within the first week of AP Chem. So, but hey, plus side is you would already know it, right? AP Chem just moves at like 3 times the rate. It's cray. So let me finish writing. I realized I deleted 5D. So you would add to the next available order of 5D, 5, and so on. Does that make sense to everybody the way I wrote it right here? 5D, 5, and so on. I can write etc. Etc. Okay, does that make sense? Okay, want to make sure the records make sense. So, honors, you're going to learn about the quantum mechanical numbers, which, I guess is the second half. I guess I put the second half. And the second way that we address it that allows to account for all 4 layers of the quantum mechanical model. Because remember, the electron configuration only accounts for the first 2 layers of the quantum mechanical model. You're going to actually draw the relative suborbitals and spin up, spin down of each specific electron's address in this secondary way of writing orbital diagrams. Okay, so that's all I have for you today, but I feel like that's pretty heavy.
Yeah.
So you guys have a lot of practice problems that you can do right now in your workbook. Honors, you have a videos that you need to watch and submit proof of completion of notes. Okay, and of course you have the quiz tomorrow. The quiz is all about what we've been learning today, yesterday, and today. It's all about the quantum mechanical model, and it's got a little bit of previous stuff, like elements, periodic trend stuff, But the real challenge is going to be this new stuff: quantum mechanical model, electron configuration, and honors orbital diagramming. Since you know that you're going to take it with a partner of my choosing, I would personally focus on the new material. You just got tested on the old material. You should be fine. Okay. So focus on the new material. There's some excellent videos I upload on my website from other people on YouTube that maybe you just need to hear it a different way. Totally fine. Okay. But you have the rest of class to do this, which is about 15 minutes. So good luck, you guys.